Hello and welcome to the video for Lecture 10, where we're going to cover sections 4.3 to 4.5 of Survey 11th edition. And the topic is going to be friction and tension forces. So just like in the last lecture video where we introduced the idea of the normal force and weight, and we did problems specific to those types of forces, that's the same idea here. We're continuing on our survey of common forces and situations where we may see those forces. We're going to see a lot of force diagrams as we solve the problems here, all right? Also known as free body diagrams. That is something that really you should be taking away from this chapter is getting used to working with force diagrams, and hopefully all of these examples I'm showing you is really showing you what it's all about. But before we get to the practice, let's get some key terms out of the way. Okay, so you already know what the normal force is, right? It is a reaction force from floors. The normal force is the force that points perpendicular to a surface and is equal in magnitude to the force pushing on that surface. Okay, so we've established that already. All right, it's also called the support force. All right, but the reason I'm bringing it up again is because if we're going to talk about friction, right, half of this chapter, friction and tension, normal force needs to be brought up again, needs to be reminded, because friction is dependent on the normal force. You'll see how. So first of all, what is a non-conservative force? That's a category of forces. It's basically friction, all right? It's also drag, which we're not talking about right now, but those are the non-conservative forces. That name, by the way, they're called that. That name comes from the fact that these forces, when present, they change mechanical energy into other forms of energy. So they make it so the mechanical energy is not conserved, hence the name non-conservative. And as I said, they changed mechanical energy to specifically heat energy. Although heat energy is a broad category that includes sound, but I don't want to go off on a tangent. Okay? The static friction force. Okay, this is the first of our types of friction force. It is the friction force acting on objects at rest. Okay? That's what defines it. All right? The name static means at rest. Okay, so the static friction force can take on a range of values for a given object, but has one maximum value for that object. So it's not, unlike the kinetic friction force, which only changes if the actual kind of situation changes, if the angles change, or of course if the surface changes. The static force will change on its own. Okay, so it's variable. It is more of an inequality than an equality. All right, and I'll explain why when we get to the key equations. All right. There's also something called rolling friction, which is just a special type of static friction. Since rolling objects have a single contact point with the ground that is horizontally at rest, the friction is static. Now, there's a lot to unpack there, and I don't want you to worry about it other than to know that rolling friction is static friction. Anytime we talk about rolling friction, we would use the static coefficient of friction. All right, I'll talk about coefficients of friction really in just a moment. Because it actually isn't sliding. Now you can have a slipping wheel. We actually don't cover it in this particular class, but that is a potential situation. So, but again, static friction, rolling friction, they're really one and the same, all right? We use the same values for both. Now finally, the other type of friction, kinetic friction, all right? So the kinetic friction force is the friction force on objects in motion, simply. Now interestingly, the kinetic friction applies to all types of motion the same, regardless of whether the motion is constant velocity or accelerating. And that's very unusual, right? We make a big deal about how constant velocity might as well be rest. You know, I mean, think about every time we do forces, every time we consider inertial versus non-inertial reference frames, we tend to loop together rest and constant velocity because what they have in common is no acceleration. And that's of paramount importance for kinematics, Newton's laws, right? I mean, here's the thing. For friction, it's the other way around. Acceleration and velocity get lumped together, and the only thing that's different is true rest. Now, why is that, right? This seems like a strange rule to remember, right? And I'd say the best way to think about it is that friction isn't real physics. And I don't mean to like make fun of it or like, try to like make a joke. It's that friction is an approximation. The actual physical processes that explain friction and cause friction would follow Newton's laws of motion and the definitions of velocity and acceleration. But the thing is that we're not explaining friction at the molecular level. We're just kind of taking a gross overview of all these molecular level processes, all these tiny little things that are happening at a microscopic scale that lead to friction, whether that's, sort of like, water forces, whether that's some sort of electrostatic force, whether that's some sort of magnetic force, whether that is just, little tiny hairs that are rubbing against other things, little fibers, all those mechanical or electromagnetic or otherwise forces, all that stuff going on follows Newton's laws, okay? So friction is not real physics. It's more like engineering, it's more like applied physics, okay? And in that sense, that's why we have different rules for it, okay? So all that aside, don't worry about it too much. Just worry that you have to separate static and kinetic friction, and you'll get used to the two cases, okay? All right, finally, what is a friction coefficient, all right? So a friction coefficient is the way we quantify friction, all right? It is the number given to particular surfaces to say how much friction they have, all right? It is a dimensionless value, so it doesn't have units or anything, neither units nor dimensions, so those go hand in hand, that depends on many properties of the surface or surfaces. I just went off on that, right? That's the idea of all the things that actually lead to friction. Okay, there are two types for any given surface or surface combination. The ones we were just talking about, static or kinetic. All right, that's it. Those are the only two types that exist, because with rolling, you would just use the static. Okay, now, why do I say surface or combination of surfaces? Because most of the time, we kind of just say, oh, the friction between the box and the concrete is this or something. Or maybe we don't even name with the type of surface. But when you actually get technical about it and you look up friction coefficients, it will say like the friction coefficient between glass on glass is this. The friction coefficient between glass on Teflon is this, right? So it's not like the surfaces of both things sliding together matter, okay? Furthermore, what should we expect for the values? What kind of values are we going to see? So you're going to notice that all friction coefficients are between 0 and 1. Technically, static friction can be bigger than 1. That's very, very uncommon. So you basically can just think of friction coefficients happening between 0 and 1. Okay, that's and they can be really small. It can be like 0.0, but they tend to be in the 0 to 0.5 range. Okay, so that's kind of where you're going to see the friction coefficients. No units, just a number. Okay, but let's see how they work before that becomes confusing. And finally, tension. What is tension? Okay, tension is another reaction force. All right, look at the way I word it. All right. Oh, by the way, before I go on, sorry. Static friction coefficients are always larger than kinetic coefficients. All right, so for any particular surface or combination of surfaces, the static case is always bigger than the kinetic case. It always takes more force to start something moving than to keep it moving. It's always harder to start pushing something than to keep pushing something. All right, maybe you've experienced that in the real life, okay? So now tension. Tension is a reaction force from ropes and strings, just like the normal force is a reaction force from floors. Okay, so very similar there. The tension force is the force that points parallel to a rope and is equal in magnitude to the force pulling on that rope. Okay? Furthermore, and we actually talked about this quite a bit when we talked about Newton's third law, when ropes are considered massless, the tension force is identical at both ends of that rope. All right? And for us, all of our ropes are massless. All right, so finally our key formulas. So here they are. This one right here is the static friction force. Notice the inequality. I mentioned that just a minute ago. Okay? It is unequal, so it's always less than mu s Fn. Okay? So why is that, right? And now it can be equal to it in the maximum case. But if it's not maximum, it's less than mu s Fn. Because the idea is Newton's third law says you push on something and that something pushes back. All right? And it turns out that the thing that pushes back creates the friction. Okay? Because that's the force pair. Object, floor, right? Or object, tabletop, And so those are your two objects. The two forces would be the force applied to move the object, and then the reaction force is the friction force from the surface, okay? Object tries to push on the floor pushes back, in other words, okay? So something like this, right? Object, floor, the object pushes on the floor in this direction, and then the floor pushes back in this direction, okay? But if the object isn't moving, the object can only, if the object isn't moving, the floor can only push back with a static friction force that is equal to whatever the pushing force was. So if the pushing force is, say, only 1 Newton, then the static friction force will only be 1 Newton, even though it could be bigger. Maybe I could push that same box with 5 newtons of force and it still doesn't move, it's still static, but now the static friction force would be equal to 5 because it would be equal and opposite to the 5 applied, okay? But at some point, the object starts moving, at which point the friction coefficient suddenly changes and now it's accelerating, okay? But that point where the object starts moving, that would be your maximum friction force, your maximum specifically static friction force, okay? And that is actually equal to mu SFN, okay? And by the way, this mu, this Greek letter with the subscript s, this is the friction coefficient. Friction coefficients are always represented by the Greek letter mu, okay? This one right here, okay? And the subscript just means static. One other thing, notice this notation used by our book, kind of this curly F for friction, the subscript s to let you know it's static. That's perfectly fine notation. I rarely use it. I'm in the habit of always writing FF for friction, right? Because I write F for all my forces, and then I use the subscript curly F, right? So definitely evocative of what the book is doing, but for a subscript rather than the actual, main script, okay? So similar notation, slightly different when I'm writing out problems, okay? And then this next one, I bet you can guess what it is. That's the friction coefficient, by the way. I bet you can guess that the kinetic friction force is F sub k, okay? And the only difference between the two is that F sub k is equal to mu k for the kinetic friction coefficient, again, always less than the static kinetic, or the static coefficient of friction. And you know what they both have in common, which I haven't mentioned so far? Is look, they're just both mentioned, or both multiplied by the normal force. So what I'm saying then is that all friction always has, in both forms, whether static or kinetic, it always has the form of a coefficient multiplied by the normal force. That is the definition of friction. All right. So the big idea here is every time you see a friction force show up in a free body diagram, every time you're writing it out in a sum of forces, an F net equation, every time you're always going to know you can substitute a friction force with a mu Fn, whether it's mu s or mu k. Okay? That's it. It's always just coefficient times normal force. Now the normal force might not just be mg, right? But we've seen that already. What if the floor is accelerating, or what if things are slanted? Refer to the previous lecture to see what I'm talking about, okay? So that's the big idea, right? We're going to be able to combine friction with other forces. We won't be doing that till the final lecture, lecture 11 of the chapter. But for now, let's introduce it. Let's see some examples, okay? But let's not forget that we're also going to be talking about tension. It's just there's no unique formulas for tension. Tension is just a reaction force. There's no formula I could write that would be like a definitive formula of tension. It just shows up when there's forces, okay? Or accelerations, or both. Okay? All right, let's move on to our practice. Okay, let's do some practice problems with friction and tension. All right, so I decided to group the problems into 4 types. Type 1, simple problems that involve static or kinetic frictions on level surfaces in one dimension. All right, so very simple, 1D, just what the heck is friction type problems. Type 2, problems that involve static or kinetic friction forces on non-level surfaces in 2 dimensions, have to take some components. Type 3, problems that involve one or more tension forces acting on a single dimension. All right, so the tension is in a one direction, okay? Type 4, fairly complex problems that involve multiple tension forces acting in 2 dimensions, okay? All right, so let's take a look at example 1. All right, you want to move a 500 Newton crate. Notice I'm giving you the weight of the crate, not its mass, across a level floor. To start the crate moving, you have to pull with a 230 Newton horizontal force. Once the crate starts moving, you can keep the crate moving at a constant velocity with only 200 newtons. Why is that? Because kinetic friction coefficients are smaller than static friction coefficients. Question A. What are the coefficient of static and kinetic friction between the crate and the floor? Because you were given enough information to find them. Notice a force diagram is drawn for both cases. Here is the weight pointing down, okay, in the negative y direction. There's the normal force pointing up, represented here by a little n, okay. Here are the friction of static and the friction of kinetic, okay. Notice this is the maximum case, because we were told this is how much it takes to start it moving. So we know it must be max, because that's the moment that it starts moving, okay. The tipping point, so to speak. All right, so we'll get back to part B in just a second. But looking at part A, for static friction, we've got our sum of forces in x and y. In the x direction, we just have the tension, which is this one here, okay, minus the static friction force. the maximum static friction force. In the y direction, we have the normal force pointing up minus mg pointing down, or w, right? But here I'm calling it mg. Those are totally interchangeable terms. And if I know w, I know m because I know g, 9.8, right? We can assume it's Earth unless we're told otherwise. We really can't. Okay? Notice, right, that in both cases, we have a 0. Why is that? Well, because in the static case, it's 0 because it's motionless. In the, and this is all static, excuse me. Well, actually, we're going to have a constant velocity, and it's still going to be equal to 0, right? But we'll get there. I don't want to jump ahead of myself. All right? So first of all, we're going to notice that the normal force is just mg. But we should expect that because the floor isn't accelerating and it's not tilted. So the normal force is mg. Okay? All right. So then we're going to substitute in the definition of static friction, which is mu s Fn. Again, that's just the definition. And then substitute in for Fn as mg. All right? And I also moved our mu s Fn over to the right-hand side of the equation so I can isolate t. All right? And then all we need to do is find mu s. Okay? All right? I suppose I could have isolated mu s, but really I just wanted to get each term on either side so I could solve for mu s. All right? I'm just kind of used to solving for tension, hence the reason I said that. Anyway, so here is the static friction coefficient equal to tension divided by mg. Mg is just weight. Let's plug in our numbers. All right, so we get 230 newtons divided by 500 newtons, 0.46. So we can really kind of see then why we expect friction to be between 0 and 1. Because look at the friction coefficient, that is. Because look at the form that friction coefficients always take. They always take in one, they may look a little bit more complicated, but they're always going to be a ratio of forces. In the simplest case, a ratio of a pulling force over a weight. Okay, they're a ratio of forces. That's why they're dimensionless, because the newtons canceled out. And also why we should expect them to be values between 0 and 1, right? Ratio. Okay, anyway, 0.46, a large but not super large friction coefficient, right? Like you'd expect from a carpet. All right, moving on to kinetic friction. So we're just going to look at the sum of forces in the x direction. All right, notice because notice we didn't do too much with the y direction. All we did with the y direction is just say, oh, well, the normal force is equal to mg, but we can make that same assumption because it's the same system. Notice here that it's still equal to 0, as I said, because there's still no acceleration, because in the kinetic case, it's still moving at constant velocity, thus no acceleration. Now, if we were to do an acceleration problem, all right, then we certainly could, and you'll see I'll do an example like that, and I think it's the next example, and then we would have an MA, we would still use the kinetic friction force. So it's so interesting, right, that for friction, we lump together constant velocity and acceleration. I know I keep mentioning that, but it's such a big strange change because we got so used to thinking about that as being a dividing line, okay? All right, anyway, so tension then is just equal to mu k mg, all right? That's exactly what we had here, except it was mu s mg. And then we're just going to solve for mu s, all right? T over mg, all right? In this case, the tension we were told was only 200 newtons because that's all it took to maintain it moving. So that means that once it starts moving, its kinetic coefficient friction is 0.4, smaller than its static coefficient of friction, all right? And then finally, part B, what would be the friction force on the same crate, on the same surface, if you only pulled a 50 newtons of horizontal force? So let's think about it. Let's just do a sum of forces, okay? So it looks exactly the same as the sum of forces for part A, right? For the first part of part A, I should say. It's just T minus static friction equal to 0 because the crate's at rest, okay? And then we're going to say, okay, well then that means that static friction must equal tension. The static friction force, because we're not solving for the coefficient this time, right? We know what the coefficient is. It's 0.46. But the static force, well, that has to be, by Newton's second law, equal to T, right? I say Newton's second law because that's what this is, right? This is F net equals ma, all right? This is the F net part. This is the ma part. But that means that here the static friction force is just 50 newtons. So how can the static friction force be 50 newtons and simultaneously be 230 newtons? Because Newton's second law trumps the definition of friction. Furthermore, I hopefully did a good job explaining that the definition of static friction is an inequality, not an equality. Right? I make a big deal about this because I've seen it confuse a lot of students. But the point being is that static friction is only what you put into it. It is, after all, reaction force. So if I don't pull that much, my static friction force won't be that big. And that also tells me that I'm never going to find my coefficient of static friction unless I keep pulling until the point it starts moving. Because if I was to try to solve this for static friction coefficient by naively replacing Fs with mu s Fn, all right, which is to say mu s mg, well, then I'd solve for a mu s that's totally different than 0.46, but it wouldn't be the true static friction coefficient, because you can only solve for the true static coefficient friction, the true coefficient of static friction when you have an equality, okay? And this, right, if it's doing that substitution for Fs, saying that it's equal to mu s mg would simply be untrue because it's an inequality, all right? Or not an inequality so much as it's a less than statement, right? Okay, so let's move on to another example. Example 2. A block of mass m equals 16.4 kilograms is in motion, it tells us it's going to be kinetic friction, on a flat surface with kinetic friction coefficient mu k equals 0.392. If a parallel pulling force is acting on the block with magnitude 111 newtons, then what is the acceleration of the block? All right, so here is our free body diagram, right? Call them force diagrams, but I tend to call them free body diagrams. We've got 4 forces to concern ourselves with. The pulling force, the normal force, the gravitational force, and the friction force. Just like above, right? Okay, level surface. There is an acceleration this time. That's a little bit different than the last example. We'll set up our sum of forces in the x direction and our sum of forces in the y direction. Again, we're not going to do too much of our sum of forces in the y direction. It's basically just going to tell us that Fn equals mg. Okay, then moving on then, we're going to rewrite the friction force as mu k Fn, okay, by definition. Notice here they're not equal to 0 because there is an acceleration, right? Because this whole thing, this is F net, okay? This part right here is F net because it is, after all, the sum of all the forces. And here's the ma part, right? That's Newton's second law. Okay, that's all, because I make a big deal about that because I don't want us to take it for granted or kind of forget what we're doing, right? We're making force diagrams, but ultimately we're just applying Newton's second law, okay? Sometimes we apply Newton's third law when we consider the relationship between forces, but mostly it's just Newton's second law, Newton's second law, Newton's second law, over and over again. Rinse and repeat, okay? So anyway, we're going to solve for the acceleration. So let's isolate it over on one side. I cancel out the m over here, all right, because I just divide both sides by m. That's all I've done in this step here. All right, let's plug in some numbers. So I got my pulling force, which is 111 newtons, divided by the mass of the object. Over here, I just have the friction coefficient of kinetic motion times gravity, right? And what do we get? 2.93 meters per second squared. Pretty fast acceleration, okay? But we are supplying a fairly large pulling force, so we're making it move quite a bit. So that's good to see because at this point, it's kind of like we keep talking about kinetic friction and velocity, but it's not like kinetic friction stops when the systems start accelerating. It just means that since there is friction, this pulling force causes the object to accelerate less than it would otherwise, right? Because otherwise it would just be 111 divided by 16.4, right? It would, because in that case it would just be a real simple Newton's second law where the acceleration was just inversely proportional to the mass and directly proportional to the net force. But here, the net force means that things get slowed down a bit, okay? All right, let's look at another one. A sled slides down a slope with a downward angle of 13.12 degrees below the horizontal. The sled has a mass of 49.97 kilograms. What must be the kinetic friction coefficient of the snow on the sled if the sled moves at constant velocity? So this is a neat one. It's going to have some way that we can solve it that makes the work a little bit simpler because there's no acceleration, because we're told that we specifically are looking for constant velocity, so that's kind of nice. But it's definitely a 2D problem. So notice we've gone from our one-dimensional friction problems to two-dimensional friction problems. Okay, here is the free body diagram. Let me get it in frame here. Okay, so here we have what's going on, right? Here is our slope. Here's the angle we were given, 13.12 degrees below the horizontal. Here is the coordinate axis that I have defined, where positive x is in the downhill direction parallel to the slope, and positive y is perpendicular to the slope. All right, here are the forces. We've got the normal force, we've got the friction force, and then we've got gravity. There's no pulling force or anything, there's just those three forces. However, the gravitational force has two components. One that kind of acts like a pulling force because it's acting in the direction that's parallel to the slope and actually wanting to accelerate the box, and then a component of the gravitational force that is pushing down on the ground, thus generating the normal force. And I say that this component of gravitational force wants to accelerate the box because it fails thanks to the friction force, okay? All right, So let's find that friction coefficient that makes sure that our sled doesn't accelerate, that it just coasts along at constant velocity. All right. So here we are. Here's our sum of forces in the x direction. It's just the positive. It's positive gravity because it's this component of gravity that points in the positive x direction as I define my coordinate system minus friction equal to 0 because there's no acceleration in the x direction. Okay? Because we were told constant velocity. We can't assume that. Okay? We can't assume there's no acceleration. We have to be told it. Now with this next one, we can assume there's no acceleration. Here, there's just the normal force pointing up and the y component of gravity pointing down. Okay? And the reason we can assume no acceleration here is you can't accelerate down into the ground. The ground is considered rigid. Okay? That's one of our kind of unstated rules here. You can't just sink into the ground unless the problem specifically tells you can. And I think that's a very reasonable assumption, right? Okay, so there's our setup. Right? Now we want to solve for mu k. Okay, but where's mu k going to show up here? Well, we got to rewrite things. We're going to rewrite the friction as mu k Fn by definition. Right here, I'm just identifying that it is k after all. Okay, but I don't always write the extra subscript, right? Okay, and now let's rewrite the sum of forces in the y direction so that we can then find mu n. Excuse me, Fn, not mu n, Fn, the normal force. Okay, because the y equation right here, the sum of force in y, is really going to help me find the normal force, won't it? Okay, so I'm going to go ahead and solve for the normal force, which is just equal to the y component of gravity. Now, be careful when you think of the y component, because this isn't the vertical component of gravity. Gravity is entirely vertical. This is the y component because of our tilted coordinate system. Why a tilted coordinate system? Because if I'd just done a normal coordinate system that was untilted, where y pointed straight up, in other words, anti-parallel to gravity, but in the same line as gravity, and x was just, say like to the right, that'd be fine. I can still solve the problem. But think about what would happen. I'd have to do components of the normal force and components of the friction force, because neither of them would be parallel to my chosen coordinate system. By having a tilted coordinate system, 2 out of my 3 forces are parallel to my axes, and I only have to take components of one of the vectors, one of the force vectors. That's the only reason I've done it, to save work, to make it easier. Why? I'm lazy. And most importantly, it means I'm less likely to make a mistake. It means you're less likely to make a mistake. Okay? So, normal force equals Fg sub y, which is just Fg cosine theta. Why do I know it's cosine theta? Because I know that this theta right here has to equal that theta by geometry. All right? So there we go. Fg, or F sub g after all, is just mg. It's always, by definition, that's gravity. Okay? All right, and then moving right along, let's rewrite the net force in the x direction. All right? Well, here, I can just move things over to the right-hand side, specifically the friction force, and then I just have Fgx equals the friction force. Now, what's Fgx? That's mg sine theta, because it's the other side of the right triangle, right? That right triangle. And Ff, the friction force, is mu k mg cosine theta. Why? How do I know that? Well, because I've replaced Fn with mg cosine theta. That means that the mg cancels from both sides of the equation, and, whoa, things are simplifying, aren't they? I can then just say mu k is equal to tangent theta. Wait, really? Yeah. That means I just plug in my 13.12 degrees, and I'm done. I found my friction coefficient, my kinetic friction coefficient. It's 0.2331. But look how remarkable that is. M and G cancel out. That means that this friction coefficient that keeps the sled sliding at a constant rate is independent of the sled that I choose. Any sled will slide at a constant rate. It is independent of the mass of the sled. I didn't even need that mass. I could have left it out. And what's more, it's independent of gravity. So the same friction would work on Mars with a different gravity, or the moon for that matter. That's amazing. The only thing that matters is the slope. Okay, so in the real world though, why might the mass matter? Well, because snow is not perfectly rigid. And if the object sinks down into the snow, that's a different dynamics. That means it has to actually come up out of the sink that it's sinking into, kind of the dent that it's sinking into as it moves. Right? So it has to actually accelerate out of that dent. That definitely changes the physics. Okay? But if the snow is perfectly rigid, then it is true that the friction coefficient is independent of the mass. Okay? Or if whatever surface you're sliding down is an approximation of being perfectly rigid, then you can say it's independent of the mass. Okay? All right, so good example there. Let's do another 2D problem. And this is a pretty neat one because it looks a lot like example 1, right? We're just pulling on a crate. But look what we've changed. We've only changed one little thing. Really, just one little thing. We're pulling at a 30-degree angle up instead of pulling horizontally. But it turns out one little change like that changes the sum of forces quite a bit and the method for solving for our unknowns. So what do we want to find? So you want to move a 500 Newton crate. It's the same crate. It's the same kinetic friction coefficient, 0.4, right? Because look, we solved for that last time, didn't we? 0.4. See, now we're using it. All right. And we're pulling 30 degrees above the horizontal. So part A, how hard must you pull to keep the crate moving at constant velocity? So that's all we're looking for is F pull. Let me show you. We just want to solve for this force. That's it, okay? Now, look, I've chosen a non-tilted coordinate axis, so the only force I have to take components of is F pull, because all the other ones are perfectly horizontal or vertical, all right? And this is what I'm looking for the magnitude of the full pulling force. I know I'm going to need to split it into components, Fpx, the horizontal component, and Fpy, the vertical component of the pulling force. All right, so let's do it. Let's write out our sum of forces. That's always your first step. That is always your first step. Write your sum of forces. Okay? Well, the first step is draw your force diagram if you need to, and if it's not drawn for you. And that if it is drawn for you, then first step is write sum of forces. If it's not drawn for you, here, being an example, draw your sum of forces first, your force diagram, your free body diagram, then write your sum of forces. Okay? All right, so F net x, what is it? Well, it's Fpx minus friction force, because that's it. That's all that's going on. Just this one minus that one. All right, simple enough. All right, what about, and it's equal to 0 because of constant velocity. After all, we were told we wanted constant velocity. What about in the y direction? 3 forces. So far, we've really only seen 2 forces, right? Because there's 3 forces in the y direction. There's one of them is a component, but it's still, a force in a sense. We have the normal force pointing up. We've got the vertical component of the pulling force pointing up. And we've got gravity pointing down. See, positive, positive, minus gravity. All right? So we're going to start with the sum of forces in y. That is usually where we start in a problem like this. All right, so then I'm going to say that the normal force is equal to mg minus fp sine theta. Whoa, that's totally different, right? Because, we actually just saw an example where the normal force was not equal to mg, and that was the tilted one with the sled, right? So we've seen when the normal force isn't equal to mg. We even saw it in the last lecture. In fact, the normal force is only equal to mg when it's on a level surface that isn't accelerating. But here we have a normal force that isn't equal to mg because we're pulling up on the object a little bit. There's an external force that's kind of lifting the object up a little bit, effectively making it lighter in reference to the ground. It's not pushing on the ground as much. That makes sense, right? Okay? So then we're going to substitute that normal force in. All I'm going to do is rewrite our sum of forces in x as Fpx, written as Fp cosine theta, because that is just the horizontal component. Cosine here is 30, which you can see behind my force vectors. All right? Then I'm going to replace Ff, the friction force, with the definition of friction force, mu k Fn, and then I'm gonna have already substituted in Fn. Okay. One thing I do is I'm going to go ahead and distribute my mu k. So there's 3 terms. Now the reason I'm doing that is because I want to solve for Fp, and so then I need to, in my next step, group my terms together that all have a pulling force magnitude in the equation. Okay, or in that term. Okay, so let's go ahead and do that. So all I've done here is I grouped my 2 Fp terms together, which would be Fp cosine theta plus mu k Fp sine theta, all right? And where does the plus come from? The plus comes from distributing this negative to that negative, and a negative times a negative is positive. If you want to practice the algebra going from this line to this line, please do so. Make sure you understand it, all right? And then another thing here is I factored out everything that's connected to the Fp value, which would have been cosine theta plus mu k sine theta, all right? And then I've divided both sides by that, okay? And let's see, oh yeah. And one other thing is that you can see is this term becomes positive, and then, oh, okay, I think I actually have, so that one should become positive, and then I should have cosine theta plus mu k sine theta. No, it should be a minus, because I am making it lighter. So let's see. All right, let's move. I'll move on with this and see if I catch it, because I was writing this one out a minute ago. I might have to leave a caveat in this part of the video about this particular problem. Okay, so let's see though. So we got 0.4 times 500 newtons. Okay, that's the mg. You have cosine 30 degrees, 0.4 times sine of 30 degrees. All right, and then solve for the pulling force, and it's 300 newtons. Okay. So let's see. So if it had been a plus, would that make sense? Because that's saying that by pulling up on it, I'm essentially making it lighter. Let's see, because let's see, I'm going to solve for Fn. So I got mg and then minus, okay. And then I have the friction force over here. I do distribute that minus, so it should become a plus. If I had been pulling down on it, that would mean I'm actually dividing by, okay, yeah, so it should be a plus. And the reason it should be a plus is because if it's a plus, then my denominator is bigger. When my denominator is bigger, my pulling force is smaller. And it should be that by pulling up on it, as long as I don't pull up on it too much, then I should be decreasing how much force it takes. So this should actually be a positive right here. This should be a plus. All right. All right. So in terms of what that value is, it should be something smaller than 300 newtons. It should be something like in the 200 range. Okay, maybe like 215 if I remember correctly. And again, I just made a mistake here at the plus. Please refer to the completed notes for the corrected version of this problem. I will correct in the notes and re-upload them so you can see what the value is of the plus. Okay? And I think I may have made the same mistake here. Let's see, because in this one, if you instead pull the 500 newtons of force, what would be the acceleration of the crate? And I think I start off, so I do my net force in x. In this case, it's no longer equal to 0. It is actually going to be equal to ma. That's the big difference, right? And the 0 became ma. All right, and then I'm going to go ahead and solve for a. I want to see if I do make the same mistake. Okay, so I have this. Yep, it looks like it, right? Because I have, well, no, maybe not. Because here so this is the definition of the friction force, mu k Fn, and then Fn is just mg minus Fp sine theta. All right, which is correct. That step is entirely correct, right? And let's see, and then I'm going to substitute it in. So let's see, so then I'm going to have, let's see if I distribute my negative correctly and make it a plus. All right, so let's see. I think I may have done it correctly here. Yep, I did. So you can see what I do is I clean this expression up a bit, and so I'll explain briefly the algebraic steps I took. And by the way, I got this acceleration directly from this equation above, just by substituting in for the friction force and dividing both sides by m. Divide that term by m, that term by m. Okay? Because the friction force is literally just this friction force is just this term here. Okay? And then Fp cosine theta is just, well, Fp cosine theta. Okay? And so then what I do is I take the shared term of Fp that shows up here and here. I distribute the negative in. So then that means that this term will be positive Fp sine theta, but it's going to be positive mu k Fp sine theta, okay, which is that right there. And then cosine theta is fine. And then that's all divided by m, because there's an m here and there's an m there. Okay. Then my last term, if I distributed this negative mu k, would be negative mu k mg divided by m. Well, then the m's would cancel, and I just get negative mu kg. Okay. But here I did not make the mistake. Here I forgot to distribute the negative, and this should have been a plus, but here I did not. Okay. All right. So this is the correct acceleration, and it ends up being, let me plug in all our numbers. All right, and notice here I'm using 500 newtons, and as written, it wasn't, I think it said 300 newtons, but when I got this value, I thought I had just come up with a number that didn't work, but actually 300 newtons would have worked if you look at the original version of the notes, and that's because this should be smaller than 300 newtons, okay? But anyway, we'll stick with using 500. All right, a last minute adjustment to the example. And so then we get a acceleration of 6.53 meters per second, which is a really big acceleration because we're pulling a lot more than we need to maintain constant velocity. So we're really speeding it up. All right, we'll say that's a really fast, short, unsustainable acceleration. Maybe just a quick burst. All right, so anyway, do expect a correction on this value. It's slightly too large because that should be positive. All right, so moving on. A sled rests on a slope with a downward angle of 25.5 degrees below the horizontal. The sled has a mass of 49.97 kilograms. The static friction coefficient of the snow on the sled, if the sled is mu s, so the coefficient is 0.0882, and that's the static coefficient of friction. The sled is prevented from sliding by a rope that is attached to a nearby tree. What is the tension in the rope if the rope is parallel to the slope? Okay, so I'm including this in kind of the 1D tension problems because the tension is parallel to the slope. So we don't have to take components of the tension, but actually this is a fairly complex problem because we have to take components of other things because it is still a 2D problem. All right, so here's our picture. It's a lot like the picture of the sled sliding down at constant velocity, but now we have an extra force. See, we have a tension force. We still have friction, we still have gravity, we still have the normal force, but we also have tension. Okay, so let's then write out our sum of forces in the x direction. I'll go faster through this one because it's similar to things we've seen before. All right, so we've got mg sine theta. That's going to be a component of the gravitational force. Specifically, it is well, this component here. Okay, and those are the two components, but it's the x component, and x is defined as downhill, just like in example 4. All right, and then minus the tension force, right? There's our new force, and then minus the static friction force. Okay, equal to 0 because it's at rest. All right, and then if we're looking at in the y direction, fix this, there we go. All right, in the y direction, it's just Fn minus mg cosine theta, and then that's going to be equal to 0, all right? Because there's only two forces in the y direction, the normal force and the y component of the gravitational force, right? The component of the gravitational force that's trying to push the sled down into the snow. All right, so then solve for the normal force, which is mg cosine theta, then substitute that into F net x, all right? So we can then rewrite the friction force as mu s mg cosine theta, all right? And then just solve for the tension force. It ends up just being mg sine theta correctly minus mu s cosine theta. All right, so there's our tension force, 172 newtons. And why should I recognize that minus is on the right track? Well, because the friction is helping the tension. The friction is doing the same thing as the tension, preventing the sled from sliding down. It wouldn't be enough on its own, but it means that the tension can work a little bit less, not literally physically work, but the tension force can be smaller than it would have to be otherwise because friction helps. All right, so there's our value after we plug in our numbers. All right, let's do another one. This is going to be one with in an accelerating system. So a pail of water with a mass of 29.4 kilograms is being lowered down a well at constant acceleration. If the pail started from rest and was lowered to a depth of 81.8 meters in 9.06 seconds, then what was the tension in the rope supporting the pail during the lowering? Okay, so what's involved in this one? Well, here's our picture, right? This is noticeably simpler in terms of forces than the previous example, all right, because it is 1D completely, right? Gravitational force, friction force, but there is an acceleration other than gravity, so I've identified it here. It's kind of a side note to the free body diagram. Positive x is defined as up. I could have defined it in any direction, but I decided to stick with up. We look at our net force in the x direction, just tension minus gravity equals negative ma. Why negative ma? Well, because we're accelerating it down. So here I'm taking into the account that acceleration points down, just as I drew in the picture. And this isn't dissimilar to the way I'm taking into account the gravitational force points down and putting the m in right there. Okay, I bring that up because I don't want us to double count the negative. Just like here, I put in negative mg, I can't then substitute in g as negative 9.8 later on, because then I would be double counting the negative. I could have put plus mg and then put in g as a negative value later, right? Both ways are totally valid. It depends on which one's more intuitive, okay? Here, it's certainly more intuitive to put the force because these forces and their directions come right out of the diagram, right? Well, I'm saying the same thing for the acceleration, okay? So now we're going to find A, because we don't know what A is. We're going to find A through kinematics, because only once we know A can we solve for tension. Otherwise, this is a single equation with two unknowns. Okay, so I'm just going to use kinematics that involve displacement and time, because that's what I was given. And then this particular equation is the right one, because then it has A as the unknown. All right, so let's think what we have here. So initial position, we can just take as 0. Initial velocity is also 0. So that means that my final position is negative 81.8, because I went down. Remember my coordinate system. And then my acceleration is negative 1/2 a t squared, and I know my time was 9.0 seconds. Notice here I've already taken into account the negative. I'm already assuming my acceleration is down, right? Just like when you write the projectile motion equations, we put negative 1/2 gt squared, okay? And so then when I solve for A, I'm solving for its magnitude, not its vector. I'm not solving for it as a vector. I'm not, because I'm already accounting for it pointing down. See, look. I solve for it as being 1.99 meters per second squared. That doesn't mean it points up. That just means that this is the magnitude of acceleration. And that also means that when I plug it back in, I will have already taken into account its negative, which means it's good that it's not negative. Because if I was to plug a negative value back in for A, having thought that I'm taking into account the negative nature of acceleration, then I would have had a negative times a negative, and they would have canceled, and I would have got the wrong answer. All right? Sign is so important, right? It's one of the biggest things you have to keep track of. And you saw above that even I can get it wrong. And I've been doing these problems hundreds of times, okay? And it's okay. You just have to do your best and get practice with it. That's the whole point, okay? All right, so anyway, then now we can finally solve for the tension force. Pretty straightforward once I, now that I have A, I just move the mg over to the other side of the equation. So it would be mg minus ma factor out the m, so then it becomes m times g minus a. Plug in my values, right? A mass of 29.4, a gravitational acceleration of 9.8, and a allowed acceleration, an additional acceleration of 1.99 in magnitude, pointing down, hence negative 1.99. And there's our tension, 230. All right, so good reality check here. Does the answer make sense? Yes. First of all, because accelerating something down effectively makes it lighter. Case in point, if this downward acceleration was gravity, this would be free fall, that whole thing would cancel, and there would be no tension. Well, of course, because that's free fall. Also, 230 newtons is smaller than the tension would be if it was supporting the pail at rest. Because if we were supporting the pail at rest, that would be like a hanging scale, and it would just be 29.4 times 9.8, or almost 300 newtons. Well, 230 newtons is smaller than 300. All right, so it all checks out and makes sense. Okay, a few more examples. Example 8. All right, this one is all about tension, and notice that this is a new type of problem. This is where we have multiple tensions, and we think about the components of multiple tensions. Okay, it's a relatively simple problem, but it's a good kind of reality check about how you can support things with multiple cables. Okay, so here we have a potted plant that's hanging from the ceiling. It's supported by 2 cables that each have an angle of 15 degrees with the vertical, as shown. Right, here's the 15 degrees, and here's the 15 degrees. This is the tension in cable 1, that's tension in cable 2. If the plant weighs 31 newtons, that would be the gravitational force, then how much tension is applied by one of the cables? All right, so then we're just going to set up our sum of forces. We've got our 2 separate tensions, and then we've got our downward gravitational force. Solve for the tension, and it's just mg divided by 2 cosine theta. Okay, plug in 15 degrees. Well, cosine of 15 degrees is actually pretty close to 1, so we're almost dividing by 2, and we get 16 newtons, right? 15.5 would have been half, right? So that means that essentially each of these wires here is carrying about half the weight. If we made the angle steeper and steeper, they'd have to start carrying more than half the weight. Okay, in that case, each wire could actually carry significantly more than the weight. How's that possible? Well, because they're trying to hold it at a really steep angle. All right, and so in that case, if you think, I mean, if I made cosine like 85 or made theta 85, then cosine of 85 is going to be a really small number, right? Well, if I'm dividing by a really small number, that means that when I take a number and divide by a small number, what happens? I get a big number. So I get a big force, okay? But here, I almost have the case where I'm minimizing my tension force. Because if both my cables were side by side and they were both vertical, then I would just be taking mg and dividing by 2. In which case the tension in the single cable would just be half of mg. All right, that's how you could just, I could add a third cable, and then each cable would be only carrying a third of mg. All right, but when it's a steep angle, it's pretty close to half. Okay, all right. Hopefully that makes sense. Let's look at another problem involving multiple tensions, some other forces. A barge is being pulled by 2 tugboats, as shown. The tension, the magnitude of tension of both tugboats is 28,000 newtons. The barge also supplies a small forward force of its own of 910 newtons. The idea, right, is that it can't, it needs the tugboats to move. All right. Lastly, the water offers a resistance force of 1,300 newtons. What is the acceleration of the barge if the barge has a mass of 850,000 kilograms? All right, so let's work this out. So we are only concerned with forces in the x direction, right? Because we're solving for acceleration, which is entirely in the x direction. All right, so let's set up our sum of forces in the x direction. So we got our 2 tensions, hence the 2. Each component in the x direction is cosine of theta, theta being 30 degrees. And then we've got our driving force of the boat, and then our resistance force of the water, and that's equal to ma. So this is a matter of solving for a, right? Here we just isolated a. We plug in all our numbers, and we get a real small acceleration of 5.7 times 10 to the negative 2 meters per second squared, which is to say 5.7 centimeters per second squared. Okay, so it's we are picking up speed here, but very gradually. All right, last example, multiple tensions, a bit more complex. Okay, a off-brand big bird stands on a tightrope as shown. If the mass of the oversized bird is 244 kilograms, then what is the tension in each side? So this is like the potted plant, okay? It's even green, but our tensions are asymmetric now. So it means that each tension won't carry the same amount of weight, all right? Let's look at it. Here's our free body diagram. Here's the gravitational force pointing down. Here's tension 1, and here's tension 2. Notice tension 2 is really long. That's what we expect. It should be a really long vector, right? Let's see why. Okay, so first of all, we need to find the angles because we were given their dimensions in length, but not the angle, right? We were given the height that the dip is 0.8, and we're given kind of the distance that the bird is from each corner, each fixed point of the tightrope, 5 and 15 respectively. So we can find out then that theta over here is 86.95 degrees, okay? And that's a testament to how it's measured. It's not measured relative to the horizontal, it's measured relative to the vertical, which is why it's such a large angle. All right, and then same thing over here, beta is 80.91, okay? So then we're going to look at our sum of forces in the x direction. So we'd have T2 times sine theta minus T1 times sine beta equals 0. That's it for our x direction forces, okay? Now, first of all, sine might be a shocker because we're so used to using cosine, but that's just because look at how our angle is defined, okay? If this is our angle, then what is going to be, what is opposite over adjacent? Well, opposite over adjacent is, is 15 over T1, okay? So that's since that's our angle, that's the, the correct trigonometric expression is sine, okay? Or I guess another way to put it is that that's the horizontal, right? Because we want this component, I'll draw it out. This would be the component of T2 that we're interested in. This would be T2x, just like this is T1x. And look at the angle, right? That's the opposite side relative to beta. And this is the opposite side relative to theta, okay? All right. And then in the y direction, we've got mg pointing down, and then we've got the two vertical components, which are cosine. Again, because, right, cosine is the adjacent side of the triangle. So T2 cosine theta and T1 cosine theta. They both point up, okay? Mg points down. And as far as x goes, one points in the negative direction, which is to the left, so one points in the positive direction, which is to the right, and one in the negative direction, which is to the left. Okay, all zeros because everything's at rest, no accelerations. Okay, so first of all, we'll solve for T2 in terms of T1. All right, so that way I can substitute it in. I think that's kind of the natural approach here. All right, so let's do that. And then once I have T2 in terms of T1, I'm going to substitute that into the F net y equation. So all I'm doing here is just replacing this T2 with this expression. So then that T2 becomes this, and that's all multiplied by cosine theta, okay? So why did I do that? Well, because it looks a lot messier now, right? Well, I did it for the simple reason is now we have one equation with one unknown, just T1. Okay, so then I can isolate T1, do some algebra here, and then we have that T1 is just mg divided by sine beta cotangent theta plus cosine beta. Where the heck did the cotangent theta came from? It just came from cosine theta over sine theta, right? And I figured I'd save space and just write that as cotangent, because after all, that is cotangent. Okay, and then I plug in all my numbers into a calculator, and I get that T1 is 11,400 newtons. Okay, that's T1. So that's this length. That's the hypotenuse. Okay, let's find T2. Well, once T2 is easy, I can just back substitute in this expression. So then it's just going to be the 11,400 newtons times sine of 80.91 degrees over sine of 86.95 degrees. All right, and that one gives me 11,200 newtons. Okay, for T2. All right. So what am I looking at here then? Well, I'm looking at my two expressions here, and I'm finding that they're both rather large, right? Because think about how much force Big Bird has here, right? Big Bird has a total gravitational force of 244 kilograms times 9.8. All right, that's only about 2,000 newtons, or maybe let's say 2,300 newtons. And then both my tensions are 11,000. They're way bigger than the actual gravitational force. How can the tensions that support the gravitational force be bigger than the gravitational force itself? Let alone because there's two of them, right? So they should share the load. The reason they're so big is because what's happening is I have this idea that the only part that's actually contributing to the gravitational force is the vertical component. Well, that means that this whole horizontal component is just there as extra force, right? So that means that the smaller the angle, this angle, or the larger this angle, then the greater the tension. Or put in really simple terms, the less slack in a tightrope, the greater that tension is under, or the greater tension that tightrope is under. A tightrope with a lot of slack, like a slack rope, I guess, would be under much less tension. Okay, so the less slack, the more tension, because only the vertical component can actually contribute to supporting gravity. Okay? All right, so that's it for examples for this lecture. Please look out for one last lecture video for this week. We'll be talking about some more force diagrams and just getting more practice with Newton's laws. All right, well, thank you so much for watching this video. I hope it's been very helpful.